You've got this very nice analytic frequency, which is the faster frequency in this pattern. And then the null spike, the bulb just kind of, like the power goes out of it, and then it resets, and then it can represent any pattern. So I think this is neat. I don't know if I've explained it very well. I hope it reveals more than it confuses. And I may still have some things wrong, but I do understand it today better than I've ever previously understood it. I may not be done learning about that. Hopefully I haven't made some huge error in what I've just said. Okay, next. Where are we doing time-wise? Okay, all right. Okay. I want to start moving in the direction of what this means, and if there's time, get back to where we were last week and connect it with that. I was going to review and set that up earlier, and then I realized that there's not, there's too much here. So I am going to skip this slide since we're running low on time, and I'm going to go straight here. This is the interpretation side. You know, the experimental part is data, and then is a mathematical analysis of the data. And this is back to the, I threw a little about the interpretation is about the attractor dynamics and about its implications for cognition. So with neural activity in primary sensory areas, he's done these analyses on areas outside of the olfactory area, and they show similar dynamics. This activity is not solely determined by the properties of the stimulus, and it's related with meaning as to how much it matters to the animal, and it's related with whether the animal's going to do anything with it, whether the animal cares. The bistability of the system for the activity, the desynchronized state or the chaotic background state, and the coherent transmitting state, and how it goes between these two. I believe the tribute written by Kozma K referred to the cinematic hypothesis as this idea of frames that occur at about a theta frequency, or in some cases a respiratory frequency in the olfactory case, and that they trigger phase cones that in some cases will spread over the whole hemisphere. They start in the sensory cortex, but in a very short time, 10 to 20 milliseconds. That's consistent with like a 50 to 100 hertz. They can move really fast, and I believe that may be a picture of a global broadcast, something like it. I don't know. The intentional arc is a description that he's puts on top of the bistable and the cinematic hypotheses, and it relates to cognition, and it's very similar to LIDA in many ways. In fact, the rhythms paper began with Stan making that observation and that connection. And I am not going to have time to get into the intentional arc right now. Let's go to some quotes which I think are really pretty interesting. The AM patterns are an early stage in the construction of meaning. They correspond to the affordances advanced by Gibson in ecological psychology, by which an animal, quote unquote, informs itself as to what to do about an odorant, such as whether to eat the food or run from the predator, giving the odorant information. They cannot represent odorants because it is impossible to match them either with stimuli or with pulse patterns from receptor activation that can convey stimuli to the cortex. Okay, so there's some useful quotes here. And this is an anatomy slide. Okay, so the sensory cortices operate autonomously in processing information. That's what the mainstream views study, the information processing, and they do indeed do that. But they operate collectively in constructing meaning. Okay, an appropriate model of cortex is a sheet of distributed coupled oscillators, like metronomes on a board. The essence of cognition lies in forming and testing expectations based on past experience. All right. Now I think there's time. Oh, I forgot about this. Found this last night, the night before. Co-authored by Detlef Heck, Walter Freeman, Robert Kozma, and half a dozen others. And I was going to read you the abstract. I think there's time. This was published in January. So it is from Frontiers in Neural Circuits. You can get it online. It's open source. Ongoing fluctuations of neuronal activity have long been considered intrinsic noise that introduces unavoidable and unwanted variability into neuronal processing, which the brain eliminates by averaging across population activity. It is now understood that the seemingly random fluctuations of cortical activity form highly structured patterns, including oscillations at various frequencies that modulate evoked neuronal responses and affect sensory perception. Ongoing cortical activity is driven by proprioceptive and interoceptive inputs. In addition, it is partially intrinsically generated, in which case it may be related to mental processes. Here we argue that respiration via multiple sensory pathways contributes a rhythmic component to the ongoing cortical activity. We suggest that this rhythmic activity modulates the temporal organization of cortical neurodynamics, thereby linking higher cortical functions to the process of breathing. Now, I believe, well, there's a number of reasons why breathing could be important, because the way the oxygen levels go up and down with breathing could affect the availability of oxygen for the very high metabolically demanding neuronal processes. But I believe there's something more to it. The way there's a rhythm to the olfactory bursts, I don't know if Freeman had the sniffing frequencies available, but Detlef has done some work on this. I think that the olfactory signal occurring at a frequency that's driven by the respiration may introduce a particular frequency. The frequency through the olfactory modality. The frequency of saccades, which is about, it's somewhere in the theta, alpha, delta range. I think it's in the delta theta range in terms of how frequently, on average, the saccades, how often we fix and create a pattern that we perceive. Have you ever tried to watch your eyes move in the mirror? If you know what saccadic suppression is. Do you know what saccadic suppression is?
Suppression.
Yes.
To keep it from happening.
It doesn't suppress the movement. It suppresses visual perception while the saccade is happening. And if you watch, if I'm examining a patient and I ask them to move their eyes to test their oculomotor muscles and nerves, I can watch their eyes move. But if I look in the mirror and try to watch my own eyes move, you will not be able to get a visual image of your own eyes moving, and that's an example of saccadic suppression. And
You
so
don't see what happens.
So I suspect, yeah, it's a mechanism, and they've worked it out that there's a frontal eye fields involved. They've worked out some of the neural mechanisms for how it happens, but I believe it could be part of a constraint on the input that's patterning the way the sensory cortex, what the dynamics of the sensory cortex are, and that some of these lower frequency signals may be related to rhythms of perception. The breathing and the saccades being two that I think are significant. It's just a hunch, and I wish I had the facility with models and experiments that Freeman had to pursue some of these hunches. I don't. At least I haven't developed it to date. But I really think that he's on to something, and I hope the scientific community can recognize what he's been on to and carry it a little bit further, because I think it's getting close to connecting with the kind of stuff we're doing. And that's what the Rhythms paper hopes to do, is to make that connection. Now, I had some things here to review. Last time, it's 5:30 now. Do we want to try to connect? Stan, do you have what's your position on what to do about, what's your feeling right now?
Well, I don't know what,
Sorry.
I'm mostly worn out,
Okay.
yeah. But I don't know what's left of her.
Well, what's left is a review of last time, which I showed you once earlier in the week. I think, why don't we just jump to here? Sorry. And see if we can tie it up here. If it doesn't work, we may have to resume. But this is Barham's figure from last week, and it's been modified with some terms from Gibson. And the light reflecting surfaces are an environmental oscillator which interact with the oscillatory system of the illumination, and that interacts with the oscillatory system in the visual perceptual apparatus and the oscillator for the action. We have high energy oscillators on the right, low energy oscillators on the left. A phase, each of these dotted lines represents the propagation of energy that starts where the phase transitions are triggered in a clockwise fashion, starting from the top right. B induces a phase transition in C, and then C and D, D and A. And so we have a dynamical system that connects the entire thing. And so for Gibsonian-wise, the optical invariants are dynamically living in the illumination, and the epistemon, this D, is predicting that the overall functional activation, if undertaken now, will be successful, and that's the affordance. And remembering that quote that from Freeman about the spatial AM pattern being like the affordance. So the epistemon, D, is like the spatial AM pattern, or the affordance. in its relation to the action. So this is a quote that we read last time and was useful, and I'm just going to read this and then I'll stop. Gibson's essential point is that information must be meaningful and specific to the control and coordination requirements of action, rather than grounding perceptual theory on brain states or as computational rules that generate three-dimensional forms from two-dimensional images on the retina. The Gibsonian program asks how structured energy distributions are lawfully related to the environments and actions of animals. And I think Freeman, the idea of structured energy distributions being related to these patterns, these dynamical patterns that Freeman identifies, and their connection to the significance for the animal and the actions of the animals fits right neatly in there. And I don't know if I well communicated what I'm seeing, but that's the best I can do for today.
So what I gathered from all of this was looking at that representation of the topographical representation of acid, that it was not same from the first time to after consolidation. So that means the representation in some sense is not same, but that is coupled to an action. And it is not needed to be same, just that that coupling should be preserved to the action. And so that's why it's not the representation in the representationalist sense that it has some features that match up to the stimulus. But the more important thing is that this activity pattern or this topographical or the states of the attractor should be coupled to some action. That's important. So that is why this is kind of the affordance to that action to which it is coupled.
I think that's about as well as I could say it. I think that's I think that's right.
So, in that sense, the title of your presentation was something about invariance. Did it say invariance in your title somewhere?
No.
That's right.
It just said Freeman's Neurodynamics and the dynamics of direct perception.
Oh.
Direct in the sense, well, there's a Gibsonian sense to direct perception.
Invariant was in one of the quotes from...
Yes, the very early quote. There it is.
How an invariant constructed by brain for photon. So there is an invariant constructed for the photon.
Right. Which is a perceptual invariant, not an
right.
Not an olfactory or
Right. So,
invariant.
I understand whatever I said before, but I don't understand what was the perceptual invariant.
The perceptual
for one particular photon, let's say the acid.
Well, it's the pattern that is like a signature, though never twice identical, is recognizable.
Right.
That's the, well, I'm not sure, the perceptual invariant is related to perception itself. The invariant, this is a neural invariant, if you will, which Freeman relates to perception.
Well, yeah,
So
I can see
it's,
that.
yeah.
I can see that. So it may be wrong to say this, but the way that Freeman was able to classify odor based on this pattern. So that is sort of an invariant, whatever the pattern is. The classification algorithm is giving you an invariant to that odor.
Yeah.
So something similar might be going on in the brain, which is creating this invariant, which can extract this odor from the pattern.
And I think the energy that is propagated by whatever's carrying the sensory modality that you're looking at, light in the case of vision, molecules in the case of olfaction, sound, what have you, that energy is like the board underneath the metronomes. It's the coupling surface, or the coupling medium, yes. It's the medium by which the dynamical activity of things in the environment,
The invariants in the dynamical activity over there are transferred into invariants in the perceptual modality.
that's right. And it is so coupled to action in the environment that, be it evolution, development, learning, whatever, the whole system of everything in the environment, the light, the energy, everything that impacts the sensory receptors, and then everything that impacts the actuators and the action in the environment, all of that is one dynamical system. And that these are attractors, these are phase transitions that propagate. So it's a very good naturalistic model that explains how cognition can exist without needing some kind of Cartesian dualism between mind and body. It puts them all in the same system, and it uses physical principles and laws to explain how cause and effect, though in a complex system, lead to this, being a feasible.
It embeds the cognition.
Cognition becomes, it becomes a dynamics on.
Yes.
Yeah. Yes. Wow. My brain is getting stretched into some Gibsonian texture, distorted surface.
I do have one question if we have time. So,
Oh, yeah.
The perceptual invariant made sense to me in terms of the examples with the olfactory bulb and recognizing a particular odor. I'm having a little bit of a difficult time making the transition over to affordance from there, meaning that it seems like
Affordance in Freeman's quote or on the diagram?
yeah, I mean, I think that in the later quote you had affordance, and then in the diagram, the Barham updated diagram, you had affordance, which makes sense because it's linked to action. But is there another step there for going? I mean, another oscillator or something like that that's in there?
Yeah. I think the brain itself has numerous oscillatory subsystems that are doing different things at the same time.
Okay. So I guess what I'm trying to get at, or trying to understand is, would the perception of the affordance be dependent upon these other perceptual invariants, or is the suggestion that you're directly perceiving the affordance even in the absence of recognizing anything else?
Yeah, I think, I would say, and I believe, Gibson or Freeman or Barham would agree, that the perception of the affordance may or may not occur. I can walk through a room without perceiving a chair that has the affordance for sitting. If my intent is to walk, then I am not going to be perceiving that affordance. Does that speak to what you were saying?
I guess what I'm more talking to is the affordance something that's directly perceived without knowledge about? I guess it would be. You don't have to really have a perceptual invariant for the kind of object you're looking at. You can perceive the affordance directly, just like these other, perceiving a smell, that's great. Perceiving an affordance, either one of those would be a direct. Yeah, I guess what I was trying to get at is an affordance a sort of a higher order thing, or is it something that is really just on par with these other perceptual invariants? And if you were trying to, if for example somebody could say,
I think it's a higher order thing.
okay,
I think, but I'm not quite sure what's meant by higher order.
so if I were to put
In this
a
context.
64 electrode grid on a olfactory bulb or something similar to this, could Freeman have stared at that and said, oh, okay, well, this is an affordance for this is yummy or something?
Yeah.
Yeah, or is it something that's more specific to the object itself that's being, so?
Well, I think see the quote begins,
That's exactly right.
the AM patterns are an early stage in the construction of meaning. And one of the things Freeman points out is that the pattern that forms in the bulb is not determined by the stimulus, it's really determined by the neurons in the bulb's interactions with each other. It's triggered by the stimulus.
But the AM patterns are also corresponding to the perceptual invariance of whatever that thing is. So that
they correspond.
Okay.
Okay, but so they are triggered by, but they are not caused by. They're not created by the stimulus. The
Right.
stimulus properties don't create the pattern.
Right. Right.
They trigger the formation of the pattern in learning,
Right.
and then they trigger its recall when the recognition occurs.
Okay. So when you were making the statement earlier about Freeman was saying that if he looked at these patterns, he could recognize that the rabbit was looking at certain things or whatever.
With a classification algorithm.
Right. The kinds of things he was classifying in that case were, okay, whether it's banana oil or whether
Yes.
it's something else. It wasn't
Yes.
something about, this is something that I want to, eat or
Well-
something like that. It was more specific.
Yeah, but see, he made those determinations in the experimental design of how he paired them with aversive or appetitive stimuli. It's like if he reinforced the stimulus, then a stimulus that the rabbit was previously uninterested in, it became interested in. If it knew it was going to get a reward or a shock,
Okay.
or if it's something like cat smelling fish, the cat
Right.
has already associated that odor with something yummy.
Right.
So
Yeah, but
So
if
that's
there was
experimentally-
some new stimulus that the cat had never been exposed to, would you get some pattern for this is yummy, even though some generalizations happening to say, well, this affordance is probably being
yeah,
assumed.
if the cat had never had an experience of a new odorant
Right.
being associated with something yummy, then it
Right.
would.
So, for example, I've never had Chinese food, for example, but I smell it and, okay, well, this is something I probably want to eat. Even though I've never had it before, it doesn't.
You're getting into a realm where there's too many possibilities for associations with past things for me to sort it out. I would say that in that case, it's going to smell an awful lot like something you've eaten. Even though
So
you
there's
haven't
something in the
spelled that
attractor
specific
landscape
thing.
that would
Yeah.
be, you'd
Yeah,
probably
you-
fit into something that might later be interpreted as yummy.
Yeah, you would already be in this is a yummy
Right.
attractor, sub-attractor,
Right.
and then there'd be some more specific attractors to, well, it's not Mexican and it's not,
Gotcha.
whatever.
Steve, I have one question. You know how we take a map of the United States, a Google map, we take all the cases of measles, place it over the map, it shows us where it is, and then we take all the vaccine that we have and place it over the vaccine for measles and place it over that. We have a 3-layer thing. And all of a sudden we begin to see things. We begin to learn things. I wonder if you could structure the mechanical 3 different layer things
Yeah.
and lay them all over each other out and look at it a while and begin to see things that you never saw before.
I wanted to do that for this and I ran out of time.
Well, it would be a tremendous job, and I'm not sure whether it would work or not, but it might be worth looking
It
at.
wouldn't take long to make a start of it where I have, with this slide, I tried to do it for.
You sort of did it on the first 2.
Yes,
But the third one didn't.
when I made this slide, I was trying to map the Gibson back to the metronomes. And, you know, and I showed it to Stan earlier, and it was confusing until I realized that I had shown him this slide first in the talk. I showed us, with my talk, I had this slide first. And yes, I mean, that's what I'm trying to do here. I wanted to figure a way to put all of them on one slide. You know, okay, we've got the mechanical metronomes, the bore, the coupling surface, and then the synchronization pattern, and then on, you know, for Barham or for Gibson, and then Freeman on another row. But I didn't figure out how to do it in time for this talk. But that's, yeah, that's what I think in your head you're already putting it together in the way that I'm trying to.
You're trying to get us to put it together in our heads.
Well, I think you're doing it, but I'm not sure I've got it done any better than you, given that you just said that. I'm really not sure that I could do a better job than you of making that
These things are
map.
called mashups, technically, when you layer complex data over complex data. And it may or may not show anything interesting. It could be a complete waste of time to go through it, or it might show you something all of a sudden that you never thought of before.
Well, can you see how these line up? I mean, if you have that intuition, can you see how these line up?
I'm not quite into it enough for you to see mechanically the various things like the metronome. I'm stuck on how I would model that to layer it over.
I hear you then. So
I don't know how to do it.
You know what I'm trying to get you to see, but I haven't shown it in a way yet.
I don't know how to do it, but I can see it's a procedural, a methodological problem.
Yeah.
Right? And I don't even know whether it's worth the time.
Oh, no.
But it might be,
Well,
because
for me
that's
it
what
would be
researchers are for, is to work out the method.
Yeah, that's what you're on to what I want to do, you know, with this talk, and it's also, I haven't quite gotten it done, so yeah.
You gave a lot of great information. It was a good one.
Thanks. Shall we? Thank you.
Okay.